This video tutorial gives you an introduction to the process of the selection of drive components. We focus here on the evaluation of the application requirements in general and the boundary conditions to respect. There is a series of further tutorials covering the calculation of key load parameters and the selection of drive components such as gearheads, motors, encoders and controllers. The selection can be divided into 7 steps that usually have to be performed in the given order. As mentioned before, there are separate video tutorials for steps 2 to 7. This tutorial covers step 1, the situation analysis, where we review the drive as a whole together with its environment. The goal is to gain a good understanding of the requirements of the application at hand. These 2 questions are the basis of all further analysis. Often I get an inquiry about a special aspect of a drive system without knowing what it's all about. How do you expect me to give a profound advice? Hence, please give us the background information as well. This is why step 1 of the selection process is so important and the raison d'être for this tutorial. Is all the necessary information available to perform a successful selection? Do we know all the relevant parameters? Dependencies between the single system components have to be identified. A checklist can be a helpful tool to make sure that all aspects have been considered. In addition, there are commercial issues to observe in order to get the business case complete. Which components shall belong to the system to offer? Just the motor? Or motor, gearhead, encoder and controller? Maybe including mechanical components and housings? How big is the sales volume? Any price indications given? Do we speak of off-the-shelf products, with modifications, or fully customized products? These 8 aspects define a given application quite well from a technical point of view. Note that they are not independent from each other, hence there's no need to go through them in the order presented here. First, operation, duty cycle, motion profiles, idle duration. Second, ambient conditions. Think of temperature, humidity, vacuum, vibration, noise, electromagnetic susceptibility. Third, electrical supply. How much current and voltage is available? Fourth, control concept. Very important. Where do the set values commands come from? What to control? Position, speed or torque? 5. Mounting conditions, which are also related to ambient, for example, cooling, but also cable length, fixation of the drive. 6. Related to mounting is the mechanical layout. What kind of mechanical transformation is used? What are the transformation parameters, for example, reduction, efficiency, friction, but also support of reaction forces. 7. How does the load look like? What are the forces that occur? Friction, feeding forces, gravity, acceleration forces. From a technical point of view, the important thing is to observe all these aspects for getting a thorough understanding of the application. As mentioned before, there are commercial issues to observe as well. Looking at the application as a black box can be a reasonable approach for a system whose components have yet to be defined. Hence, the first question to answer is not what is in the box, but what are the inputs and what should come out, and how does it work? This black box here is a tunable elastic robotic joint. It has all kinds of ingredients. However, during analysis of the application task, we are rather interested in the interfaces. Concerning power, on the input side of the black box, there is the electrical supply with voltage and current. For DC power supplies, there are different possibilities, including batteries, accus, solar panels. The output power is given by the required load motion. Here one can differentiate between linear motion with force and velocity and rotational motion with torque and speed. Current and voltage must match the need of the drive system. how much voltage is required, and how much voltage is available, how much current is required, and how much current can be delivered. The mechanical concept and the bearing systems are also part of the motion output. The drive types adapts the output from motor or motor gearhead to the needs of the load. Two different drive types can be distinguished. Linear or translational drive types such as spindle drive, rack and pinion, and conveyor belt convert the rotational motion of the motor into a linear motion of the load. Rotational drive types, all kind of gears and belt drives, transmit a rotational movement to the load. A full mechanical description includes bearings and guidances which must be capable to support all kinds of reaction forces. They are also important for the estimation of friction forces. The orientation with respect to gravity might also be a valuable information. The required motion can lead to different load scenarios. Basically, these four operation modes can be differentiated. Continuous operation. Here the drive accelerates once and moves with a constant load for a long period of time. Examples are laser beam deflection or a tattoo gun. Short-term operation. Intense load during a short period of time followed by a very long standstill. An example is an insulin pump, one shot every few hours. Cyclic operation is characterized by a relative short variable load profile, however, continuously repeated. Typical examples can be found in production equipments such as pick and place. Cycles may also vary as in a strapping tool. On-off operation is a special case of cyclic operation. The weakest link in the drive chain limits the power available at the load. Hence, it's not only the torque and speed limits of the motor. The limited torque capabilities of the gearhead or the mechanical system must be considered as well, or some current limit of motor, controller or power supply. Similarly, the achievable speed can be limited by other components such as sensor, gears and mechanics or controller. The voltage capabilities of controller and power supply might not be sufficient to reach the required speed. Observe, there are constraints imposed by the hardware or by the software. The second black box aspect is control. What is the motion task? Positioning, speed or force control? Where do the commands come from? What should be the quality of the motion? What is the position accuracy, the speed accuracy? How fast controlled? Consider the following points. Which is my parameter to be controlled and how is it measured? Accordingly, a matching sensor type has to be defined. Are there additional sensors needed? How is the information passed on to the drive system? Is there a supervisor or master system? If yes, how does this higher level host system communicate with the drive? For example, via CAN open or another field bus, or via a serial interface such as RS-232 or USB. Set values could also simply be given as a digital or analog signal. Do we need additional in- and outputs, for example for homing or temperature monitoring? Additionally, the range and the needed accuracy of the controlled parameter has to be defined. Again, the weakest link in the drive chain and the combination of it all defines the quality of motion. Typically you would say it's the sensor resolution and sensor accuracy that gives a perfect control. But this is just one element. A lot depends on the design of the control loops and on communication between components, and on the available power for a fast reaction. A lot depends also on the mechanics, the masses to be moved and other damping mechanisms. But then we also have the ugly things such as backlash, mechanical play, elastic behavior, non-constant friction, resonances. Achieving high-end control is a matter of well-balancing all system components in the given ambient. Based on the task and the consideration about control type and communication made so far, the possible types of Maxon controllers can already be defined. The DEC is a simple speed controller typically used for applications such as roller blind drives, blower or pumps, or cutting and grinding appliances. The SCON is a very versatile dynamic current and speed controller. It can be used when the requirements about control performance are higher, as in drives for conveyors and all kinds of handheld tools and scanners. The EPOS is the standard solution for positioning and/or if bus communication is required. Typical applications include all kinds of actuators, laboratory automation, door drives and similar. MaxPOS is a high dynamic and fast controller, requiring a high-speed EtherCAT master system. It's perfect for demanding multi-axis control, such as in robotics, pick-and-place, and on-the-fly processing. The last black box consideration of our application covers environmental aspects and boundary conditions. Generally, the interaction and interference with the ambient. On one hand, any system has emissions that influence and even disturb the environment and surrounding. On the other hand, any system is susceptible to ambient conditions. Some special conditions and requirements include temperature, noise, vibration and shock, sterilization, ionizing radiation, electromagnetic interference. Space applications combine a lot of these special ambient conditions, including vacuum. Particular boundary and mounting conditions may strongly influence the type and the costs of a drive. Usually the maximum drive dimensions defines also its maximum power and its price. The service life of drives cannot be calculated exactly. It strongly depends on load cycle, application and ambient conditions. However, a service life estimation is possible by means of experience values from similar applications. The expected service life is usually given as service hours or number of working cycles. Having defined all these aspects gives us a very good general picture and understanding of the application from a technical point of view. Add the commercial information and you are ready to continue with the next steps of drive selection, which is a closer look at the required load forces and speed. This is it for step 1.